So thanks for coming, everybody. I know all of you, kind of. I'm Tarek. I am going to be giving a few talks. I'm not exactly sure how many. We'll sort of go over that in a little bit. But I was itching to learn about some new stuff, and it's useful for me to talk about it as I'm learning it. So that's what we're going to be doing. And the idea is that I want to keep things simpler and more conceptual this time. And I want us to be able to think about things, right, and feel things, and really to get a sense of what's going on. And I know that in med school and in a lot of school, we get kind of the thinking taken out of us, right? We just want answers and just sort of facts and fact-based. And I want this to be not fact-based. And I might say some facts. In fact, I'm probably going to get some facts wrong, and that's not even really important. Correct me if I'm getting them wrong. But the idea is how we want to think. And I'm going to try to engage you guys more in these talks than I have before. I'm going to have some breaks, usually at least one or two. In this one it's two, so we'll talk for maybe 20 minutes or so, and we'll talk for 10 minutes, right? So I'm hoping that that helps me a bit and also helps you guys kind of give me feedback and think about things differently. So more videos, more back and forth discussion is what I'm hoping. I'm obviously going to be talking more than you guys, but I'm hoping that you guys are participating as well. So the other big reason I'm giving this talk, and we don't think about this a lot as residents, but Dr. Hobbs probably realizes this more, is that we are actually kind of powerful, influential people, and that's kind of like, you know, cheesy to say, but it's true, right? We're going to be doctors or whatever, other things, and we're going to have money, and we're going to have power, we're going to meet a lot of people, and people are going to listen to us. And you know, when your first therapy patient comes back and says, well, I really thought about what you said, and they did something differently, you start to realize that, you know, we are in a position, I think, as doctors in general, but also as psychiatrists particularly, to take a stance on things, whether it be politics or you know, mental health-based things or whatever. So you know, I think my idea is that I've got a platform to ramble it to you guys, and then you guys can maybe take some of that information and think about it, and you know, it can all amplify outward. So I'll give you my crazy, and then you can filter it, because there's some goodness in you know, I come at things often very with hyperbole and with excess because it's fun, but there's often something true in what I'm saying, and that's kind of what I'm getting at. So I guess I also want you guys to be critical of the science, right? To understand that there has to be some factualness below this. You know, we can do away with just the tyranny of randomized, double-blind, placebo-controlled trial. I've talked about that before. It's valuable when we know how to use it, but it can also be really misused. And I think it is misused a good bit in medicine, and I think what we end up seeing is kind of the manipulation of math and money in medicine. You can make things look the way that you want them to if you were smart about designing a trial and playing with numbers, and you need to be very careful. And so that's really what the main goal is. And then I'm very passionate about this stuff, as you guys will see. And I don't think, you know, the goal is that I want you guys to be able to think well and to be able to stand up to like the businessmen and the politicians and the sycophants, and you know, that's not everybody, but that is people who have a lot of power. And the idea is that, you know, we don't want, you know, copycat drugs, right? We want creativity and new thoughts and novelty. We want to be able to, you know, think for ourselves and come to these conclusions. So we want to be able to, I'm going to take a step back and kind of talk about what are the big goals, right? So I want us to be able to focus on what's important. That's ultimately thinking in a more effective way, and to be able to use that thinking to do good. And so what do I sort of, as my big thoughts, think we can do to help with things? So I think we can focus on money on science, money on the arts, and money in education. I think if we can do those things, we'd be off to a good start. If we can understand the importance of relationships, right? Family, friends, distant strangers, and really realize how connected we all are, I think that would help people bridge some of the gaps we have, right? We talk about the family tree, and then we talk about the tree of life, and you know, it's not a analogy that's fake to say they're the same thing, right? We are all related in a very real biological way, and you know, to understand that we have a lot more in common with people than we think, and we really, you know, if we were to change our perspectives, I think that would help a bit. And I think the third thing, which is probably the most important but also the hardest, is to provide opportunities and environments for people to be able to grow. Opportunities conducive to growth, right? Because I think that's what we need to kind of push towards equality. So that's kind of my soapbox hippie talk, and we'll dive more into what we're doing here. So to get back to this stuff, I'm not an expert at this, right? You guys know that. I have the same training that you guys have. I'm getting this information on my own through different sources, so I'm definitely going to make mistakes. Some stuff is not going to be right. Correct me, like I said, I'll do my best to correct myself, but also getting at the point that that doesn't really matter, right? If I'm talking about, I'm going to go over chemistry a little bit and brief organic chemistry, and I'm going to talk about electrons moving, all right? If I see an electron comes here and breaks this bond and comes here, and really it goes in a different order, right? It doesn't matter, like it's wrong, but the idea that what I'm going to be talking about is the underlying principles, right? And that's hopefully going to be right, and if you take that away, that's what I'm looking for. Also, we got to ignore some exceptions, right? So I'm going to say blanket statements that are not going to be true in every situation. So things like, every gene makes a protein, right? That's pretty much true. I'm not going to have time to go through every single, subtle example of where it's not true. But do you guys have, and this is, again, I'm just going to start, and this is the way I ask things. I'm going to ask them to give you 3 seconds, and if not, I'm just going to answer it on my own. So what's an example of a gene that does not make a protein, ultimately?
At the very end, the repeating...
Okay, so telomeres?
Yeah,
telomeres. Okay, I wouldn't call them genes. I might call genes things that are expressing a protein. So ultimately, you're going to get... Well,
80% of it.
I just sort of went back to what I was saying, circular argument. Genes are going to be something that make RNA, at least. They're going to get read by RNA polymerase. So most of the time it goes to protein. An example, for example, would be ribosomal RNA, right? It's going to end there. Ribosomal RNA is not going to make a protein. So anyways, that's just an example of, I'm going to say all genes make a protein, but it's not true, right? But you get the general point of what I'm saying. So what's going on here? What do you all think when you see this? Math. All right, good. Okay, so math in general, but give me more specifically. Yeah, you're right. That's what I'm getting at. It's going to be a math analogy.
Formulas.
Integrals.
Integrals. Okay, so you're talking about one. Integrals here, right? Integrals we usually associate with calculus. So what this is getting at is building in foundations, and this is something that I talked about last time. How we learn things stepwise, and at each step, each chunk is manageable. It's not really that hard, and once you learn it, in retrospect, it seems easy, right? So 2 + 7, none of us are going to struggle with that. But there was a time when we did. But once you've learned it, it becomes common sense, and that allows the next step to be possible. So when you have a foundation, you can take on the next level of complexity. And from algebra, we could all do this. With a brief review, we could all do geometry and trig, into integrals. And then, things can get crazy, right? Does anybody know what this equation is? Not that it matters. So it's Schrodinger's equation. And it looks really, really, really intimidating. But here's a secret that nobody's probably ever told you, but is definitely true. Pretty much anybody can learn and comprehend this. Okay, you guys can learn and comprehend this. It takes a little bit of time. It takes understanding the fundamentals, and it takes some motivation, right? So the secret here is that geniuses really aren't geniuses, okay? Geniuses are no smarter than you guys, I promise you. They're probably smarter than me, but the point is that rocket science isn't rocket science, right? It seems complex because you need to know a lot of fundamentals to do it, but when these guys are doing it, they're just doing this, right? They're not, the people out there aren't making these eureka genius. They're just doing their fundamentals, and it looks really intimidating to us, because this looks really intimidating because we aren't fully comfortable with all the steps up to it, right? And we could give tons of examples for this, whether it be sports or playing a musical instrument or whatever. Once you know how to do it, right? Once you know how to draw it, it's so obvious. But until you do it, everything is so foreign to you. It's not able to be, it's just overwhelming if you were to just jump into it. So that's the idea. I want to focus on the fundamentals, right? And so what I want to teach you are some fundamentals of science that will let us answer some questions in psychiatry. Because the questions in psychiatry, from a science standpoint, blow away Schrodinger's equations. And I will say, with a fair level of confidence, that psychiatry, understanding it on a basic science level, is probably one of the most complicated things in the world. I think, puts rocket science to shame, right? Rocket science is simple, I don't want to hate on rocket scientists. They're obviously smart people too. You get some, math, you get some engineering, you get some physics and materials, and you can make rockets. using equations, using basic science. Explain to me love on a basic science basis, and I will be quite impressed. I'll be impressed if that happens in my lifetime, because it's complicated. It's very, very complicated, because it's so complex, and that's what we're getting at, is that we want to get the basics to boil the complexity down a little bit, right? So when people talk about serotonin, we have a framework to put it in, because without it, we can start making assumptions, and those assumptions may or may not be correct. So this lets us test our assumptions against things. So that's what's the point of learning these things. And it gets to the idea of, and I said this before, if I've seen further, it's because I've stood on the shoulders of giants. It's so true, because what these people are really saying is, look, we realize we're not that smart. We're not smarter than the guy before. We're just working, right? We're just grinding. We're just using this stuff in every single step. I don't know if you remember when you were in math class. Every single step they say, oh yeah, that's obvious. Oh yeah, that's obvious. But when you look at the big picture of things, it's huge. But that's what science is. You just grind a chunk at a time, and it's the giants from behind that let us do these crazy, awesome things. And so that's what we're going to try and do. We're just build that foundation. So a quickie on what we're going to do. The first 5 or 6 are going to be very basic science. Physics, chemistry, biology, genetics, okay? This is going to be super condensed. I'm stealing it from a bigger course, so it's going to be very condensed. Then we're going to apply that to the neuron, okay? About 4 to 6 lectures on that. We are going to learn a lot about a neuron, but that's still going to be just an intro to it, but a good enough intro to give us a sense of it. I can actually give these lectures. I feel very confident giving them. I'm probably going to be able to answer your questions. It's not too difficult once you know the material. After that, it's going to get much more difficult, right? Because I'm going to start talking about behavior. And, first I'm just going to talk about neurons in general, so plural, so brains, how our senses work, how neural modules work, how behaviors work, how chaos and emergence comes to be. That's going to be tricky. And then we're going to ultimately try and apply it to really behaviors, complex human behaviors in the context of an environment, in the context of growth and learning. And I don't know how far we'll get. I'm sort of thinking about 16 to 20 talks if we can. I'm sure we'll get at least into the 3rd lecture set, and we'll just sort of see. The other thing before we dive into it is copyright stuff. So I don't know the copyright law. I'm obviously stealing a lot of material. I think it's all public domain, but just as to start us off, I'm going to give a bibliography of most of the sites that I'm getting it from. Assume that if I'm saying something, it's not mine. I'm stealing it from somebody, because in some way or another, it's probably not genuinely mine. I really don't want to take credit for people. I try to give credit when I can, but that's just sort of a caveat. All right. So I mentioned this book to a couple of people. It's The Machinery of Life by David Goodsell. He is a molecular biologist that works at the Scripps Institute, and I read this book. I just stumbled across it. It's very cool. This guy is a watercolor artist, and he makes these paintings of the cell. And I like the book so much, I bought it for my mom, and she read it, because I'm trying to get her to think critically. And it's embarrassing how much my mom comes up with these talks. She liked it so much, and so for Christmas she contacted him and asked him if she could buy a painting from him. And he says, well, he doesn't have any originals. So my mom bought a poster from him, and I will hand that out, and you guys can look at it. But who knows what this is?
It's a Villas or something, isn't it?
Yeah.
I picked it for a reason. What do you think these things are?
It's a
Nervin terminal?
Yes! Excellent. Remind me of your name. I knew that.
Kelly.
Kelly, I know that. I've been to you several times. It's embarrassing. So it's the vesicle, so it's a synapse here. And so it's drawn with incredible accuracy, actually on the X-ray structure. You guys can pass it around or whatever. And we're going to look at a lot of his pictures, and I think that's okay to do. But he actually painted me one, because my mom asked him really nicely. He painted me a watercolor ribosome, and I've got it framed. I didn't bring it because I didn't have enough hands. So anyways, I want to give him props. That was very nice of him. And I think the one thing that we forget often as doctors is to encourage our doctors, right? Encourage our fellow scientists and doctors to do more. We talk to patients all the time, but we can use some encouragement too, right? And so that was very nice of him, and he didn't have to do that. And so I think, the more scientists can get people engaged, and that's what part of this education is getting you thinking about this, maybe giving your own lectures, that sort of thing. All right, what else did I bring? I've got a lot of props this time. All right, so what we're going to do here is talk about how we learn, right? So Piaget was a child developmentalist who studied learning, and we learned about Piaget by Dr. O'Prey, and you guys haven't gotten him yet. One of you has. Some of you have. he's a very, very, in my opinion, a great teacher. And he said one thing that just has haunted me in the best way possible, and it's play with it, right? When we have a difficult concept come up, he says play with it. And that just has not ever left my head. And I've really learned that we learn things by playing with it. So this is silly putty, right? And it's obviously kind of getting at the idea of conservation maths. And please open it up and play with it. And please open it. And the idea that we learn things by coming at them open play.
It's a trust issue.
Go for it. Absolutely. Wing it at me if I'm lying to you. By manipulating things with our hands is how we get a sense of the environment, right? We start to learn how things work. The cell, we can't do that with, and that's what I'm going to try and do. I'm going to try and have us dive into the cell. So I'm going to talk about how we're going to get in the world of the cell. The other thing that I like about play is that it implies fun, right? If this isn't fun, I know it's not a ton of fun, but it needs to be at least a little bit of fun. It needs to get you curious. It needs to get you thinking about it. Because then your mind is right. It's right for learning things. The other thing is we have to be kind of challenged about it and come in it with an open mind, right? We need to let go of things and just sort of be willing to accept new things. You know, run, fall, scrape your knee, get back up. That's what we're going to be doing here. This is very difficult for me. I'm not, very comfortable with this stuff, and I stumbled through this a lot to finally try and get a sense of it. And I find myself catching what I'm saying a lot to get a sense of things, see what I'm saying, hear what I'm saying. I'm using those words unconsciously, but they mean something, right? We experience life through our senses. Everything is built on our senses from a simple basis up. And so that's what we want to do, right? We want to feel the cell, see the cell, hear the cell, and that's what I'm going to try and get you to do with some of these fun experiments that we're going to do. This is just a book that I read as I was going through the Sapolsky lectures. I'm going to talk a couple of things about it briefly, but life is pretty much what you get when you're on the border of order and chaos, right? Chaos is just craziness. Order is boring, right? It's wrong. We are chaos. We are this unpredictable, we're not just chaos, we're at the border of order and chaos. This is the main textbook, that doesn't show up well at all, that I'm using for the genetic stuff. I talked to some of you about this book. It's where I'm going to get most of the network stuff for the brain. This is one of the most inspiring science books I've ever read, and probably one of the most inspiring books I've ever read. The author's actually got a very cool story, but it's an excellent book. I recommend anybody reading it. It's accessible to anybody. You don't need anything but like a basic sense of science to understand it. These are coming out pretty poorly. Principles of Neuroscience is where most of the course is going to come from. It's this huge, big, fat book, but it's actually a great book for being a textbook. I'll give the chapters out if anybody wants to follow along. That's doubtful, but this is where, this is a UC Berkeley course that I'm stealing a good bit of the first few lectures off of. It's given by 3 different guys. It's 40 lectures. I'm going to condense it into about 4. So very clearly, I'm stealing from them and condensing their stuff. So it's Marcus Pauly, Robert Fisher, and David Weisblatt. So giving them credit for it. I steal a few other slides, not many, but just want to give them credit for it. I've gone through a few just different, OpenCourseWare stuff is very cool. You can get access to this. I'm just sort of showing it because a lot of the information is coming from this stuff. They have just full courses online. I have to put up an obligatory Robert Sapolsky. I'm not going over this stuff this time. We went over some of this last year, but I know he has just kind of influenced me enough that eventually I'm going to say something that is just absolutely stolen from him. And if you really want to make the most of your lectures here, what I kind of recommend you all doing is just getting up, going home, and watching his lectures, because it really is just impressive to see him talk. It's almost unhuman. He makes teaching kind of like an art form. It's just he takes these complicated ideas and breaks them down so lucidly and makes it fun. And he's got like the best dry sense of humor ever. But they're really very much worth seeing. A few other lectures that I'm going to steal some of the sense stuff from is the How to Use lectures. You guys, Wiki, donate, right? I get a lot of stuff from Wikipedia. I talk about them a lot. Scholarpedia is newer. It's actually Olaf Sporns is related to the family of Scholarpedia. They get world experts writing wiki for the stuff, right? So pretty much the amygdala site is going to be written by the amygdala world leader, and it's pretty impressive. Lots of this stuff's from YouTube. I'm going to be pulling videos up. Google, obviously I get some of the information. So it sounds like a running advertisement. We're done at this point with this stuff. I just want to sort of get all of this out of the way. All right, so now kind of formally onto the course. So the first talk is going to be on scale. So I'm going to start with a ruler, and you all can just sort of look at it. I mean, you all have a sense of what a foot is and what a millimeter and a centimeter is, but we're going to be using this a good bit, right? So what we're going to do is we are going to magnify the size of cells a million times. Okay, so to do that we have to have a sense of what these sizes mean, right? So we know a millimeter is really pretty small, okay? Does anybody know what a micron is? How many microns or micrometers are in a millimeter?
Millions of values.
It's a millionth of a meter, so how many microns are in a millimeter? You probably said the right answer.
10 to the third.
10 to the third, or
1,000.
1,000, yes, okay. If you think in 10 to the third, that's beautiful. That's right, so 1,000 microns are in a millimeter. How many nanometers are in a millimeter?
10 to the 6.
10 to the 6. 10 to the 9 nanometers in a meter.
Yeah.
So a million. Okay, so if we're magnifying by a million, a nanometer size structure is going to be if we're going to make a nanometer a million times bigger, how big are we going to see a nanometer in this cell world?
Let's see. Let's see.
But if we make it a million times bigger so that we can see it, that's the idea. I want you to be able to see these things. It would be a millimeter.
Yeah.
Okay. So a million nanometers is a millimeter. A million microns or micrometers is a meter. Okay. So something that is a nanometer, I want you to see as a millimeter and look on that, thing going around for what a millimeter is. Something that's a micron is going to be a meter. Okay. So let me give you a few examples of this. All right. An atom is an angstrom, a carbon atom, roughly, and then these things blur out a bit at the edges. So that's a tenth of a millimeter. That's about as small as we can see. Okay. Now you can look at that and almost see a carbon atom. Okay. Now glucose. We know what glucose is. It's a hexose sugar, right? That's what we get our energy sources from. It's a millimeter. You can see that there. Okay. DNA, 2 nanometers wide. We're going to be 2 millimeters in our world, and 3.5 millimeters per turn. So I really want you to look and see that. See DNA and see it spinning. And see the sugar phosphate backbone. Nobody's doing this, they're all just looking at me. Really try and see it in your hand. And see it spinning and see the bases. Okay? Mitochondria is about a micron. Most of our organelles are roughly a micron. So they're going to be about a meter. All right, so here's our mitochondria. Okay? We can see it here. It's really here. All right? Our proteins, like insulin, it's a small protein. It's 5 nanometers. That's 5 millimeters. So we can see now we've got these big things. A cell is roughly 10 to 100 microns. All right? That's getting to be 10 meters to, that's about the size of this room, to the size of a football field, but circular. All right? So now you can see in this room you've got a mitochondria and you've got DNA, teeny tiny, and proteins that are a centimeter in size roughly. That gives you a sense of scale of what's going on in the cell, and it's filled with water and other things too. Okay, so that's what we're going to be looking a lot at this hour. So just as an interesting fact, a neuron that goes down to stimulate the motor in your toes would be 1,000 kilometers long. All right, and the neuron can send a signal like that. That's like from here to Florida, literally in less than a millisecond. So if you think about that scale, what we're doing is really, it's amazing. When we start seeing what these molecules can do with speed, it's amazing. So why does size matter, right? The reason that size matters, and we're going to get to this more, is that every single process that happens is a consequence of charge and shape. All right? That's the way the world works. You need to get access to things, distance to things, and charge. That's where every single force that you're used to, besides gravity, is electromagnetic. All right, we're going to get back to that. But everything, pushing, pulling, friction, everything is electromagnetic when it gets really down to it. So we're not going to get that deep, but that's really what's happening, is that these charges are interacting. So the idea behind that is that size matters, right? If you ask a mechanic to fix your car, and he's dragging the 6-foot wrench behind him, you're not letting him anywhere near your car, right? Clearly, he doesn't have a sense of how the system works. You need to have an idea of size and relation and forces to be able to diagnose and treat, right? And that's what I'm getting at. We want to have a sense of size, of how to manipulate things, how they get manipulated to treat these things. So now we're going to go on a journey. If this works. Please work. Okay. Some of you may have seen this.
Yeah.
Oh, we get sound too. Okay, so we're going to zoom way out. So we'll just start here, and it's at the human. Now I'm going to zoom way out to the universe, and it's got our 10 scale so we can get a sense of things, okay? So we can literally zoom out to the edge of the universe here.
Yeah, I saw it on your thing, and I
And
spent time on it too. Just the median molecule.
it's not gonna, one thing I want you to keep in mind is there are no gaps, right? Because in reality, there are no gaps anywhere. So this is all continuous. So here's our universe at 10 to the 27, right? We zoom in, don't have a lot of time, but we can obviously stop and we're starting to see galaxies at 10 to the 20. There's a few fun ones. It's worth looking at this, but for time's sake, I'm gonna scroll through it quickly, okay? We've already gone huge orders of magnitude. We're, getting, there's one, the Homunculus Nebula. That's awesome. Right, 10 to the 13, we're already still in galactic kind of terms. We're looking at sort of planets. Here, there's Saturn, you can see, and now we're getting into things that we recognize, okay? So here you can see Earth and the USA, right? Good old red, white, and blue. Zooming in, now on 10 to the 6th, right? Which is megameters. We can see California, Italy, Grand Canyon. Zooming in, 10 to the 4th, things that were sort of, the Large Hadron Collider, I didn't know it was on there. I got a picture of it coming up at some point. So a kilometer here, right? These are things we're now familiar with. This is where it's going to start to be where we're talking about, right? So where we live, a meter, right? That's the scale that we're on, is the meter. Getting in here to different kinds of small animals, right? Here's 10 to the minus 1, okay? Pencilette at 10 to the minus 2. Zooming in, right, amoeba, that's a single cell, we can see that. That's a single cell visible by the naked eye. That's one of the bigger single-celled organisms. Now starting to get pretty small, right, to the level of cells, 10 to the minus 5, that's 10 microns, right? That's what we've been talking about. Zooming in more, E. coli, the X chromosome. Zooming in even more. The smallest thing visible to an optical microscope, right? Smaller than the wavelength of light, you can't see it with light. It's impossible. It's against you can cheat a little bit, but you can't go much smaller than that. DNA, right, like I was talking about, the 2 nanometer thing, right? So again, you can see it if you blow it up a little bit. And so everything below it here is what we're talking about, blowing up and seeing in this appreciable way. Phospholipids, or alpha helix, glucose, right? We talked about these things, a cesium atom. Now I'm just going to jump in really quick, there's water, and actually show you how deep it goes, all right? So we're getting pretty darn small, right? And just certainly into quantum levels, we're way past that at this point. But if you notice, at 10 to the minus 35th, which is a Planck length, there is more dimensionality inside your body than there is outside of it related to the entire universe. So I just want you to keep that in mind. There is more scale variation of physics happening inside our body than there is outside our body in the entire universe, which is just kind of fascinating to me. All right, so we'll be done with that. And, all right, that worked. That music was relaxing. All right. So discussion. Okay. All right, so let's see where we are on time, 4:40. I will try and be fast so we can get some of this done. Let's just talk about a couple of these things. Let's just talk about other examples of things that work, like fundamentals, right? Just think of an example, whatever you guys want to talk about. Something that's really complicated, maybe to you or maybe to somebody else that's really simple to you. I can take this off the video if that makes it more meaningful.
Something that's a building block,
Something that works on the concept of building blocks.
neurotransmitters.
Neurotransmitters, right? That's not something that's like intimate to us, but you're right. Neurotransmitters are one of these building blocks of ridiculously complex things. What about in the world that we live in, right? Something like playing guitar. Starts ridiculously complicated, but as you build in each step, you learn. And then at the end, you're an expert, piano concerto player, and it's sort of easy. But at any single step, anybody looking at that views it as kind of crazy. What else? What are other things that we build?
Language?
Language, that's a perfect example, right? It's constantly sort of expanding, learning the simple words. If you just look at a child, what are they doing? We speak now completely fluently. They're building it, right? They are having to force these connections, but then it happens naturally. sports, right? You build the fundamentals, throwing, hand-eye coordination, running, how the game works, and all of these things. Most things that people look to be geniuses at are really taking very complex phenomena, breaking it down, building up their bases in those, and then reintegrating it, right? That's what you do. When you're training, I don't know anything about sports, but that's what they do when they're training. They isolate different things, train them up, and then get them back together and have them play ball. What else? Any thoughts that you guys have when we sort of saw the size thing or anything like that? Anything interesting that stood out? Thoughts on education? Do we do it well? Do we not do it well? Things that could be different?
Terry's lectures.
Maybe
Those are
not
building
on
blocks.
the spot. They could be building blocks. They're building blocks for me,
Yeah.
right? For sure. All right. So let's get into, these are David Goodsell pictures. So we'll look at a few things and then we'll try and wrap that up. So I'm going to try and show you scale by using an example of molecular machines solving problems. All right. So this is E. coli. It's a micron. Okay. How big is a micron going to be in our world that we're going to live in? A meter. All right. So here's E. coli. Right. This thing out here. It's a meter, right? We can see it. It's got flagella here, which are appreciable in this world, right? They're physical. These are not fake, okay? They're real things that turn in the exact same way that a propeller would turn. It's working on the same physics, but they're a bit trickier. So this is real. That kind of blew me away. I say this as if it's like, people say that, like, why are you so excited about this? These things didn't click to me, that like, this is really like a machine. It's like a car, but way cooler. So here it's zooming in, right? We're going to zoom in on this here, and this is about 100 nanometers wide. So when I talk about problem solving, okay, I'm going to be talking about three things. Intelligence to me is three things. You take in information, you process it, and you do something with it, okay? People argue what intelligence is. That's what my working definition of it's going to be, right? So I want to get away from an anthropomorphic view of intelligence, where intelligence is this abstract thing. Problem-solving intelligence is what I like to think of as intelligence. You take in information, you process it, and then you act to solve a problem. And there's lots of different ways to do that. So we're zooming in here. This is 100 nanometers roughly by 100 nanometers. We can see already, right? This is our flagella that we're talking about. There's cilia, there's cell membrane, plasma membrane, DNA, ribosomes. And then we can see here, we're zooming in again. This is this area here being zoomed in. This is about 10 nanometers, okay? So here we are. This is 10 nanometers by 10 nanometers. How big is that in our world? 10 millimeters by 10 millimeters. So it's a square centimeter, okay? So I want you to see this picture in a square centimeter, all right? So I want you guys to guess at what these things are. What do you think this is? I mean, and there's, I don't expect you to know these things. We haven't gone over any of this yet, but just take a guess. What do you think this might be? In just a broad category, you don't need to be specific.
Organelle.
Okay, it's a protein. So we're at the centimeter layer, right? So our mitochondria is out here, and I really appreciate you venturing out. But what this is going to do is let us make educated guesses, right? Because once we can start thinking about scale, we'll start to see that, oh, well, no, an organelle is going to be bigger. But we've got to dive in, right? And it's better to guess, like I said, because then you're thinking about it, right? And you're stimulating. It's a protein. Okay, so if this is a protein, it's a Krebs cycle protein, whatever, it's not too important to us. This is mRNA, all right? What do you think this aqua colored stuff is?
Water.
It's water. Yes, okay, great. So look at it, they're different colors. Okay, there's a darker one and a lighter one, all right? What do you think the darker one is?
Oxygen.
Oxygen. This is an atom, okay? So on this scale here that we're looking at, 1,000,000 times blown up, you can imagine if this is in here, teeny, teeny, tiny, you can see an atom, okay? And what do you think the lighter colored one is?
Hydrogen.
Hydrogen, okay. So here we go. This is a metal. I'll just go ahead and tell you it's iron. What do you think its charge is?
2+.
2+, probably, right? It could be other things, but it's positively charged. Look how these water cells are arranging, all right? David Goodsell knows what he's doing, all right? He's not just making stuff up. Why is it taking this confirmation? This is 2+. I heard something, that's right.
Negative oxygen.
Negative oxygen.
oxygen.
It's happy, right? Thermodynamically, it's happy, okay? So we're going to talk about like happy thermodynamics in a bit. This is a happy, it likes to be here. I want you guys to use this new knowledge to look at a random thing and answer a question, which you'll be able to do. Look at these, I don't know how well you can see it. Look at these waters. What side are orienting inwards towards the green thing? Positive, they're hydrogen. So what charge do you think that thing is? Negative, right? So looking at the sense of scale, what do you think that might be? Now, I mean, you don't have to get this perfectly right, but what do you think it might be? Chloride, right? So look at what we can do. We can start to really make sense of things based on what we know, all right? So these are sort of phosphate groups. I'm just going to go over them. Maybe stuff like glucose or amino acids or ATP or whatever, all right? So let's see, here we go. So this is the cytoplasm. All this is in the cytoplasm, all right? So what we're going to do is we're going to make cytoplasm. If you all are ready and we have power, and I should probably shut the door if we're going to make a mess. I need an assistant here who wants to help.
Jill.
Where do we have power to pull from? All right.
So these are not margaritas? What you're gonna make?
We talked about salt
Do you
and.
want to set me up, Joe?
Yeah.
I'm sorry.
Yeah.
Close.
All right, so we're going to put stuff in here. Can somebody get a video on this? Can we get a rotation? Oh, I didn't bring water.
I think we have water somewhere.
Okay, so we've got protein, okay? Right, we've got proteins in there.
Yeah.
All right, what else do we have in there? I mentioned some sugars. Right, we've got sugars.
Not really sugar.
I told you, I'm not going to be factually accurate. Let's see. The idea behind this is that I want to show you it's not water, and the consistency isn't water. This thing got breaded, but it's a chicken wing. We've got some protein powder, right, because we need to be fit. So that in there, that's important. Probably cover these here. All right, what else is in the cell? Right, we've got lipids. This is extra virgin olive oil. It's not soap. I use a soap container. All right. We don't have water. That's unfortunate. Can I use your tea? Well, I've got a better substitute, right? So like any good stressed person, it crosses the plasma membrane readily, right? Because it's polar, and we'll go over that. It's polar because it's got a hydroxyl group. Sure. All right, so let's see what we make here. I'm not sure how well this is going to blend. There's about 70% water to 30% proteins, okay? And just to keep in mind, an egg is 90% water to 10% protein. And you know how gooey an egg is, right? So I want you to understand, this is not light. It's actually very dense, and that's going to have a lot to do with how these things move around.
What was the percentage you said?
This is 70% water, 30% proteins.
In the bottle is water or alcohol?
And this one?
Yeah.
It's Bud Light Platinum.
Okay.
It's water.
The
answer is 90%.
All right, you've got the honors.
Bud Light.
You've got the honors.
Oh.
Alright, ready?
Give it a go.
Oh.
Is that one high? All right. So as you can see, I wanted to get a thick consistency. I don't know how we're going to do.
I don't think the chicken.
All right. What do you think? How do you think? Anybody want to taste?
Kelly's really thirsty.
Oh.
I'm actually very surprised. I was expecting. Anyone's welcome to try it. Honestly, don't get any of the chicken, but besides that, it's not bad. Thank you, Joe.
Is that raw chicken?
It's actually not bad. No, it's
Okay.
Red Lantern chicken. Full on advertisement. All right. So remember, it's not water, right? It's thick, and that's actually important. You've got to imagine these things sort of spinning around in a thick, viscous fluid. All right, so we just want to reorient ourselves to the zoomed in. So this is our flagella motor. I've got a video on it. I'm not sure if you guys would rather me send out the video or you'd rather me play it. It's about 5 minutes long. Because I wanted to get through, which would you guys rather me do? Play the video showing this flagella?
Yes. We don't need to watch.
Okay.
Yeah, you can send it out.
Yes.
So
send it.
what this is here, I just want you to see that this is a machine, a molecular machine, okay? And the way that it works is that this is the motor, pretty much. Okay, this is the rotor. So this is the power stroking part of it. This is the rotor, and this is the flagella that spins. This is a sensing protein, and this is a soluble molecule, okay? So the idea is that there's a whole bunch of these things, if you can remember, and you're just going to have to trust me at this point. You'll see it on the video, that by a conformational change, this is powered by hydrogen. We'll talk about different energy currencies that the cell uses. One is electrochemical, which is hydrogen, right? ATP synthase uses hydrogen to power a rotor to create ATP through a conformational change. This creates a stator to power these power strokes. Literally, it looks like an engine. In fact, we've created these engines on a macro scale, but they don't work great. To spin this rotor, which is through the membrane, to then spin the flagella, okay, and it can spin in two directions. This thing can spin up to 18,000 RPMs, although under load it typically spins like 1,000 or 500 or whatever. So you've got all these flagella coming out, okay? If it spins in one way, they all loop together and they form one thick flagella that spins and propels this thing forward. If it rotates the other way, rather than looping together, the flagella all splay out and kind of do this thing, which lets the E. coli tumble, okay? So it has two options, right? Two motor options that it can do. We've got a lot, right? It has about two. It can either move forward or it can tumble, all right? How do you think it picks which one to take?
Least resistance.
That's one possibility, right? That's a very good guess. What do you think E. coli wants to do, right? That's kind of what we need to ask. What's the motivation for this behavior? That's what we'd ask in psychiatry, right? What's the motivation for this behavior? Why would anything want to move? What are the main things that life wants to do?
Find food.
Yeah, it's find food. That's exactly why. So it wants to decide where to go based on where is their food. And survive, right? Survival, we need food. So it's got a sensing protein that can sense gradients of food. If it's liking what it's seeing, it says, keep going ahead. If it's not liking what it's seeing, it releases this soluble protein, binds to this, and it switches direction and it tumbles. Let's find a new direction, right? Look how elegant that is. It works amazingly well at locating food sources. This is intelligence, okay? In the biological world, this is intelligence. This is problem solving that we have only recently found out in the past couple of decades. There are problems that bacteria can solve, that ants can solve, that humans have only recently been able to solve. And I talked about some of these in my last lecture series, like traveling salesmen, right? They can solve things through chemicals that we have not been able to solve with all of our brains, with all of our computing power until recently. And there's still probably examples of that. Think of what bees can do with their pathfinding, with their efficiency, and it's done in these sorts of ways. So that's the idea of what I want to kind of get you all thinking about, is how can these small proteins solve problems? Because that's what they're doing, okay? The other thing that I want you to think about is that it's a different world. So E. coli can move at 30 microns a second, okay? So it is a micron. It can move at 30 times its body length a second, okay? And it stops in the length of a water molecule, all right? Completely different world. That would be the equivalent of us traveling 40 miles per hour in a car, really faster than that, and stopping in less than a millimeter, okay? Not the world we live in. But they live in a different world. There's something called a Reynolds number, which looks at inertia and viscosity, right? And so the inertia is its resistance to change, and viscosity is the resistance of the fluid to change. Water doesn't want to change. That water is actually very densely packed. E. coli is fine with changing. So as it's moving, it's powering through because it's got a motor behind it. But when it stops, it's instant. That water hits it like a brick wall, and that gives it very different properties that lets it do things very differently. Again, to just sort of think about what's going on, because we're going to talk about that. These proteins in our cell, in that cytoplasm, are bouncing around, and it's not like they're moving in water. They are moving in water, but not in the sense that we think about it. Right? When we swim, we realize, oh, it's kind of, we're fighting against it. This is bouncing around a million times before it kind of gets to maybe where it needs to go. It's hitting things and strongly bouncing off based on momentum in this medium. So let me, I guess, say as a caveat, and this is maybe a good way to try and wrap up, I do not think that this is how psychiatry works. Okay, I do not think that we are going to get any answers of a psychiatric phenomenon based on a protein. I think these things matter. these things are going to be the underlying basis of what makes things tick. But just like electromagnetic forces are how we pick things up, that's not the world we operate in, right? A mechanic works on your engine. He doesn't have to be a PhD in thermodynamics to understand how an engine works. He needs to know the nuts and bolts of it. So yes, all those properties underlie what the mechanic's doing, right? They're still there, but he doesn't have to know them. The currency of psychiatry in practice is not going to be this. It's going to be at a level above this, really, at one or two levels above this, really. But those processes are influenced by what is happening here, right? And what we are going to try and do is bridge that gap. I can actually give you a solid basis of what's going to happen here. The bridging of the gap is more difficult, but it will let us challenge the misconceptions that are out there and think for ourselves and actually don't want to go out too far on a limb, but think for yourself in ways that are actually better than what people are doing. Even experts are saying. So I will send this movie out for you guys to see, and then I'll just wrap up by showing you a good cell picture. This is the neuron that I've passed around. You know, again, we can get another appreciation for this, of how it's all working on this scale, and then to just relate it to what a textbook might look like, right? So the detail here, it's not really even up to par of reality. And this is what we'll see when we see a picture, right? We'll maybe see, if we're lucky, alpha helices. But now if you go back and look at this, right? This is binding of the neurotransmitter vesicle, right? This is really happening. When it's separating, it's truly a molecular conformational change that's doing it. And now you can see back here, you've got these same proteins, right? And they're literally taking this plasma membrane and fusing it with the plasma membrane at the end of the synapse. So I will end there, and when we start back up, we're going to jump right into doing a little bit of housekeeping, and then we'll jump right into physics and chemistry. And so I've got the introduction out. I'm glad to have done that. Do you guys have any questions?